Our story begins in the Taurus Littrow Valley on the Moon, December 1972. This was a place unlike any other, a dramatic landscape of towering mountains and deep valleys, bathed in the stark sunlight of lunar day. Here, the final chapter of the Apollo lunar landings would unfold, marking a turning point in humanity's exploration of space. Apollo 17 astronauts Eugene Cernan and Harrison Schmitt were the last humans to walk there. Their footsteps, imprinted in the lunar dust, remain undisturbed to this day, a silent testament to human curiosity and courage. Their mission was more than planting a flag. They were field geologists, collecting samples to unlock the moon's ancient past. Every rock and grain of soil they gathered was a clue, a piece of a puzzle that scientists on Earth would spend decades trying to solve. They explored a valley shaped by volcanic eruptions and impacts, gathering rocks and soil as scientific treasures. The landscape told a story of violent forces and slow transformations written in stone and dust. Among their tasks, they hammered a hollow tube deep into the lunar soil, extracting a core sample, a layered history of the moon. This was painstaking work, done in bulky suits and low gravity, but it was essential for understanding the moon's evolution. This core, taken from a landslide deposit near Lara Crater, held a mix of rock types and ages. It was a time capsule, preserving evidence of ancient volcanic eruptions and meteorite impacts. The astronauts knew these samples were more than souvenirs. They were fragments of another world's story. Each sample was carefully documented, packed, and prepared for the long journey back to Earth. The Taurus Littrow Valley was chosen for its complex geology, promising clues about the moon's volcanic activity and formation. Scientists hoped that by studying this region they could better understand not only the moon, but the early history of our own planet. Apollo 17 returned with the largest haul of lunar material, fueling decades of discovery. These rocks and soils have been studied by generations of scientists, revealing new insights with each passing year. Unbeknownst to them, one core sample would remain untouched for half a century, waiting for future scientists. It was sealed away, a gift to the future, to be opened when technology had advanced enough to reveal its deepest secrets. They collected data not just for their time, but for ours, planting seeds of knowledge for when technology could ask deeper questions. Their work laid the foundation for discoveries that would come long after their return. The dust they packed away preserved secrets about the Earth-Moon system, waiting to be unveiled long after their footprints faded. These tiny grains hold clues to the processes that shaped both worlds. The legacy of Apollo 17 was not just in exploration, but in the promise of discoveries yet to come. Their journey reminds us that every step forward in space is a step toward understanding our place in the universe. The journey of these lunar samples didn't end with their return to Earth. Instead, their story was just beginning, as they became some of the most carefully protected scientific treasures in human history. At NASA's Johnson Space Center, these precious rocks were stored in pure nitrogen to prevent contamination from Earth's atmosphere, preserving their original lunar chemistry for future generations. But a select few, including a core from the Taurus Littrow Valley, were sealed under vacuum right on the moon itself. A true time capsule, untouched by earthly influences for decades. This sample, known as Core 73001, preserved not only the rock but also volatile gases and delicate minerals exactly as they existed on the lunar surface, offering a pristine snapshot of the moon's environment. For 50 years, it remained sealed, a silent witness to lunar history, waiting patiently in the darkness of NASA's vaults for the right moment to be revealed. NASA's foresight in saving untouched samples was a gift to future science, ensuring that as technology advanced, new generations could unlock secrets the Apollo astronauts could only dream of. This became part of the Apollo Next Generation Sample Analysis (ANGSA) program, a groundbreaking initiative using today's most advanced technology to answer questions that have lingered since the dawn of lunar exploration. In 2022, after decades of anticipation, scientists finally opened Core 73001 in a lab filled with pure nitrogen, exposing it to modern analytical tools, never to Earth's air, ensuring its secrets remained unspoiled. For the first time in half a century, this ancient material was ready to tell its story, offering clues about the moon's past and the history of our solar system. The opening bridged the legacy of Apollo with the frontiers of 21st century science, connecting the dreams of the past with the discoveries of today. The gray dust, last touched by cosmic light billions of years ago, was now a key to new discoveries, holding answers to questions we are only now able to ask. A lunar time capsule, finally unlocked, its secrets ready to inspire a new era of exploration. With Core 73001 open, scientists unleash the power of modern technology, diving deep into the mysteries of the moon. Today's instruments, like secondary ion mass spectrometry, SIMS, are far more sensitive than anything from the Apollo era, offering unprecedented precision. SIMS fires a beam of ions at the sample, blasting off atoms for precise analysis, allowing scientists to delve into the atomic structure. This lets scientists identify not just elements, but their isotopes, unique fingerprints of cosmic history, revealing stories untold. Isotopes, like those of sulfur, reveal subtle clues about a material's origin, tracing back to the very formation of the moon. Researchers focused on microscopic volcanic glass beads in the lunar dust, tiny droplets from ancient eruptions, each holding a piece of the moon's fiery past. These beads trapped chemical information from deep within the moon's mantle, offering a glimpse into its hidden depths. By analyzing their chemistry, scientists glimpsed the moon's interior, uncovering secrets buried for eons. The precision of SIMS allowed them to study sulfur isotopes in individual grains, preserving their original signatures and painting a detailed picture of lunar history. This level of detail was unimaginable in the 1970s, a quantum leap in reading the moon's story, transforming our understanding. The ANGSA program's patience paid off, opening a new window into lunar history and showcasing the power of modern science. Modern science could finally decode secrets locked away for billions of years, secrets that were once beyond our reach. The moon's past was ready to be rewritten, with each discovery adding a new chapter to its ancient story. Analyzing the volcanic glass beads, scientists found something startling in the sulfur. On Earth, sulfur isotopes exist in predictable ratios, but the moon's grains were different. The anomaly centered on sulfur-33, which was significantly depleted compared to other isotopes. Scientists measure this with delta-33s. Earth's standard is 0, but lunar values were strongly negative. This wasn't a minor difference, it was a clear, unique fingerprint. Other markers, like oxygen isotopes, show Earth and Moon are chemical twins, supporting the giant impact hypothesis. But this sulfur data told a different story. Deep inside, the Moon is fundamentally different. The signature was locked inside volcanic glass, meaning it came from the lunar mantle, not surface contamination. This was a primordial signal preserved for eons. The mystery deepened. What process could create such a unique sulfur signature on the Moon, but not on Earth? The answer could reshape our understanding of lunar history. Why is the Moon's sulfur so different from Earth's? Earth's geology, plate tectonics, volcanism, water, mixes materials thoroughly, creating uniform sulfur ratios worldwide. The Moon, smaller and geologically quiet for billions of years, never mixed its interior as thoroughly. Ancient pockets of material could remain distinct, preserving early solar system chemistry. The strange sulfur signature may be evidence of this incomplete mixing, a fossil record of the Moon's formation. While Earth's history is erased by constant change, the Moon preserves clues from planetary infancy. The sulfur anomaly suggests the Moon's building blocks weren't identical to Earth's, or that unique lunar processes left a permanent mark. This difference isn't just a curiosity, it's a window into divergent planetary histories. Earth became dynamic and evolving, the Moon, a frozen archive. The sulfur anomaly highlights this split, revealing a chemical memory Earth has long lost. The Moon's quiet preserves what Earth's activity erased. Its sulfur tells a story our planet can no longer remember. Where did this strange sulfur come from? One theory points to the young Moon's surface. Billions of years ago, volcanic eruptions may have created a thin, temporary lunar atmosphere. Intense ultraviolet sunlight could have triggered chemical reactions, altering sulfur isotopes, especially depleting sulfur-33. This photochemical process left a distinct chemical scar on the surface. But how did this altered sulfur reach the deep mantle? Some models suggest early lunar overturns could have buried surface material deep inside. Later, this material melted and erupted as volcanic glass beads. If true, the sulfur signature is a relic of ancient sunlight and a dynamic early moon. It hints at a world more active and complex than we once imagined. The second theory reaches back to the moon's birth. The giant impact hypothesis says a Mars-sized body, Theia, collided with Earth, forming the moon from the debris. If Theia's chemistry was different, especially its sulfur isotopes, some of its unmixed material could have become part of the moon. These pockets preserved in the lunar mantle could explain the sulfur anomaly. If true, we're not just studying the moon, we're holding a piece of Theia, a lost world from the dawn of the solar system. The sulfur signature would be Theia's fingerprint, preserved in lunar dust. It's a direct link to planetary building blocks from billions of years ago. This discovery could reshape our understanding of the moon's formation. For decades, the moon was seen as a well-mixed twin of Earth, born from a homogeneous debris disk. The sulfur anomaly challenges that view, suggesting the moon's interior is a mosaic of different chemical domains. Whether from Theia or early surface processes, the moon is more complex than we thought. This finding forces us to refine our models of the giant impact and lunar evolution. The moon isn't just a chip off Earth, it has its own unique inheritance. The power of sample return missions is clear old rocks, new questions, and a story still unfolding. The moon's true origin is more nuanced, and the search for answers continues. A few grains of dust have sent us back to the drawing board. The sulfur anomaly is just the beginning of a new era in lunar science. Scientists will now search for this signature in other lunar samples and Apollo missions. If widespread, it could confirm a fundamental feature of the moon's interior and Theia's legacy. The ANGSA program proves the value of preserving samples for future technology. New missions like Artemis will target unexplored regions, seeking more clues. Each new sample is a step closer to understanding our origins. The moon, once thought familiar, still holds profound mysteries. Its secrets are waiting for us to ask the right questions.